Hi guys, in this video we will be talking about electric field and force. So in the previous chapter we talked about charges, and today we're going to talk about electric field and electric force. So what is electric field? So basically when you have a charge, it is basically going to create a field around it, and it's basically going to go all around. So that field, so this region, is basically called electric field. And what is the reason for the electric fields? Basically a charge. So any charge is going to create their own field. An electric field is shown by capital E. And as you can also see, the darkness of the lines are basically determining the strength of the electric field. So as you go farther and farther away, your field is basically getting weaker and weaker. All right, next thing is Coulomb's law, or electric force. Charles Coulomb was the guy who invented the attraction in between the charges. So we said like charges repel each other and unlike charges attract each other. We talked about that. But since they're basically attracting and repelling, then we're talking about push and pull. So we're talking about force. So in this case, we are going to call this electric force. But what is the relationship in between the charges and the force? So basically, when this Charles Coulomb made the investigation, he figured out that charge 1, charge 2, and it doesn't matter what the sign is, so that's why we have this absolute value. You basically increase the charge and then the force increases. So if either one of them increases, the force increases. And the other thing that he observed was the distance. As you increase or decrease the distance, then the force is also changing. But he recognized that when he doubles the distance, for example, when this distance is d, and when he doubles the distance to 2d, if the force in this case is F, then he figured that when the distance is doubled, it is less force, but doubling the distance didn't halve the force, but it actually decreased it by 4 times. So when he made the distance 3D, he recognized the force decreased by 9 times. Then he basically was able to put that relationship as the square relationship, but it is inverse square because as distance increases, force decreases. So it's going to be basically underneath. And the other thing that we have in the equation, when he did the calculation, he was always figuring out that there's an extra number. And this extra number is basically Coulomb's constant. And this Coulomb's constant is a large number. It's 9 times 10 to the power of 9. So then we expect the force to be really high because this K itself is pretty high, but the scale of charge is going to be in the nanoscale or microscale. So that's why we are not going to be able to actually observe really high forces. So that is the equation for force. And this equation is basically known as, or this relationship is known as Coulomb's law. Alright, so if you have more than one charge in the system, then what's going to happen? Then what you do is, let's say in this case we are talking about the force on the third charge. So what you do, you basically figure out the force in between individual charges, so Q3 and Q2. So what is the relationship in between them? One of them is positive, the other is negative. Then we will know that they're going to attract each other. So then we basically draw the vector, force vector in between the second and third charge. So it is going to be towards left. And once we look at 1 and 3, so we are done with 2. And now we have the first charge and the third charge. So we're going to look at the force in between those first and third charge. And then when we look at it, we are seeing that they are the same charge. So they're going to repel each other. So the force is going to be basically going away from the third charge diagonally. So these are the forces acting on the third charge. But if they are asking basically what will be the net force on charge 3, then what we need to do, we basically have two forces acting on the object. So one is pulling in this direction, the other is pulling in this direction. Then we basically add those two vectors together. So when you add those two vectors together, basically adding it to the end, if you guys remember how we add the vectors together, so you add it over here, then the final direction of the force is going to be basically going towards in this direction. So that's how we find the net force if you have more than one object in the system. And if you need to make calculation, then what we do, F13 is going to be calculated as K Q1 Q3 divided by distance squared, so which is square root of 2a squared, and the force in between 1 and 2 would be K times Q1 Q2 divided by distance, which is a squared. Alright, and you basically find individual forces by using the charges and the distances in between them. Alright, so we have an example. So we have a charge negative Q right here. And then they are basically asking for Q, let's call them numbers 1, 2, and 3. So Q1, Q2, and Q3, they're basically acting on this negative Q. What will be the net force acting on the charge? So what are we going to do? We are basically going to think about each force created by each charge. So let's start with the first charge. So negative, positive. So they're going to attract each other. So the first force that we have in between Q and then the first charge is going to be going in this direction. So let's call it F1. And the force in between 2 and the charge that we have is negative here. So it is going to basically along this line, because this is the straight line in between them. And since they are the same charge, they're going to basically repel each other. But it is not going to be as strong as the other one because the distance in here is less than here. So F1 is going to be greater than F2 in length. And the next one is Q, negative Q and positive Q. Again, what's going to happen? They are going to create an attractive force. So this is also going to be going towards the third charge. So we basically have those three forces. So we have basically F1, we have F2, and those two are the same length. How do I know? Because charges are the same, distances are the same, so that means they're going to be the same force. But this guy is going to be a little bit shorter because charge is the same, but distance is more. So this vector is going to be less than the others. So now we have F2 and F1 together. So what we need to do, we also need to put them together. So once we put those two together, what are we going to observe? They're going to be actually going in this direction. So F1 plus F2. So this vector is even larger than the F1 and F2. So that means it's definitely longer than F2 itself. Sorry, that should be F3. F3. So what does that mean? The total, the final direction, the net force acting on the charge on the left corner is going to be basically going diagonal down, which is C. Alright, two isolated charges Q1 and negative 2 are negative 2Q. So Q and negative 2q, and they are separated by 2 centimeters. If F is the magnitude of the force acting on negative 2q. So once we look at those two forces, two charges, one of them is positive, the other is negative. So what does that mean? One is they're going to attract each other. So on negative q, the force is basically towards left. So, and it is going to be F, that's what's given, because they say the force acting on charge negative 2q. And they're going to attract each other, so that means on 2q the force is left and the magnitude is F. And the question is, what will be the force on this positive q? So what we know about force, action-reaction pairs are always the same, but they're going to be acting in the opposite direction. So that means this q will be basically pulled back towards negative 2q, but the value is still F, because force is basically Newton's third law. Action-reaction pairs are equal to one another. So it's not A or B, so it's going to be F. It's not E either. And it is going to be basically going towards negative 2q, so it's going to be C. Alright, an electron and proton of hydrogen atom are separated on the average by a distance of approximately 5.3, 10 to the power negative 11, and find the magnitude of electric force between two particles. So, we basically have electron, and then we have proton, and then they're basically asking for the force in between them. And a way for us to find electric force is basically as follows: K Q1 Q2 divided by distance square. So the distance in between them is given. It's 5.3 times 10 to the power of negative 11. So we are talking about electron and proton. So we definitely know the charge for both. Charge for both is the same, and it is 1.6 times 10 to the power of negative 19. This is negative, this is positive, but remember, positive, negative doesn't really matter. It is just in an absolute value. So I didn't put the absolute value in here, but you have absolute value over there. And basically, we are just going to put the numbers together, and then we're going to do the calculation. So K that we have is another constant, and it is 9 times 10 to the power of 9. And the Q1 is 1.6 times 10 to the power of negative 19. And then Q2 is another 1.6 times 10 to the power of negative 19. And the distance is going to be 5.3 times 10 to the power of negative 11. But you need to be careful, because it is not just the distance, but the distance square. Alright, so we just need to solve this final calculation. So here, there's nothing extra. You just need to be able to multiply and divide those numbers. The only messy thing is a lot of numbers and huge numbers. So I advise you guys to use calculator in this case. And then I advise you guys to multiply the numbers first. So on the top we have 9, 1.6, 1.6. So we're going to be doing the powers later. So 9 times 1.6 times 1.6. So what is this at the end? 23.4. So you will have 23.4 or 04. So this is the number that we have with from just the numbers in front of the powers. Then what are we going to do? We are going to be adding the powers differently or separately. So we have 10. So they all have the base of 10, and we have basically 3 different powers. So since they are in multiplication, then we are just going to add the powers. So we will have 9, negative 19, negative 19. And then you divide with 5.3. So it is square of it. So 5.3 square, it is 28.09. So 28.09 times, remember, you are taking the square of 10 to the power of negative 11. So that means this 2 and negative 11 must be multiplied. So your power for the bottom is negative 22. And then you are going to do the math here separately, math here separately. So let's look at the numbers. Whoops. So let's divide the numbers first. So 23.04 divided by 28.09. So that gives you 0.82. So 0.82 times, then we are going to be basically dealing with the power. So negative 22 in the bottom is going to go to the top as positive. Then all we need to do is basically add the powers. So plus 9 minus 19 minus 19. And negative 22 in the bottom is going to become upstairs as positive, so plus 22. So as you can see, our final number is negative 7. So it's going to be 10 to the power of negative 7. So our force in between proton and neutron, if the distance in between them is that close, the force is, as you can see, pretty small, because it's 0.82 10 to the power of negative 7. So that's how we do the math in between them. Do the numbers separately, do the powers separately, and then you will be able to find the answer. Alright, so charge of Q and negative 4Q situated as shown below. A test charge is placed at points shown below. The net force on the test charge is 0 near at which point? Well, we didn't talk about test charge yet, but test charge is basically the smallest charge ever that you can have. So we are trying to figure out the net force being 0. So let's think about, and the other property of test charge is it is positively charged. So that means you're going to be putting a positive charge at those 5 different points. And then let's try to figure out so we are going to have those charges, and we always have 2 other charges that is acting on them. So let's think about it. So if you put a positive charge at point A, so you have positive, positive, so they're going to repel each other. And let's call this as the first one, and then this is the second charge. So F1 is basically going left. And then if you look at 4Q and the test charge is positive and negative, then they're going to attract each other. So the force of pulling is going to be in the other direction. So it's going to be F2. So there's a possibility that this F1 and F2 are equal to one another, and basically the net force is 0. But let's think about point B. So positive and positive. So what will be the force in between them? It's going to go in this direction, so F1. And then positive and negative. So that is also going to go towards right. So in between, it doesn't really matter actually where you are at. It doesn't matter if you're B, C, or D. You will see that any force, any charge in between those two charges, they both are going to have F1 and F2 together towards right. So there's no way that those two added together will become 0. And you can also get the same idea over here. F2 will be F2 because this is negative, this is positive. F2 will be towards left. Positive, positive is going to go towards right. So point E is also a possibility, but now we need to think about the distance. Because when you think about distance, remember the force and distance are related, and as you go farther away from the charge, you're going to have less force. So, and the amount of charge is also effective. So we know the first charge is pulling weaker than the second charge, because second charge is 4Q, the first charge is just Q. So then we are going to know that F1 is less than F2. So F1 is less than F2, F1 is less than F2. Then what is the other thing that we can actually put into the equation and then try to make them equal? Distance. And as you get farther away from the charge, then you're going to have less force. And if you're closer to the charge, then you're going to have more force. Then what should we actually think about? We should think about weaker force to be closer, right? Because if you are closer, then you're going to have extra force. Then this F1 and F2 can be equal. So because of the charges, F1 is less than F2. Then if we place the charge closer to the weaker charge, then F1 is going to be more than F2. Then that means it is possible that those F1 and F2 are equal to one another, and net force acting on this charge is 0. But if you think about point E, 4Q is more like creating a greater force, and it's also closer to the charge. So that means F2 is way larger than F1, so there's no way that these two are going to be equal to one another. So the answer will be point A. Alright, point charge is basically or test charge. It has 0 size, and the charge of this guy is the charge of a proton. Alright, so it's 1.6 times 10 to the power negative 19 coulombs. And the charge is positive, and it is shown by Q0. Alright, that's the definition of a test or point charge. Alright, so what is the relationship between electric force and electric field? So when the test charge enters to an electric field, so when do we have a field? When we have a charge in the system. So when a test charge, that smallest charge, enters to a field, then what is going to happen? It is going to actually feel a force. An electric field, the measurement of electric field is basically how much force you have on that charge. Alright, so force per that unit charge or point charge is going to be the number of electric fields. Alright, it's going to be the value for the electric fields. So electric fields is two ways: force divided by the point charge that you put, or the test charge that you put. Or if you think about the force, so you have Q and Q0 in the system, then if you think about the force equation, electric force, it is K Q Q0 divided by distance square, right? Or R square, both the same. So this is electric force. And if you divide it with Q0, then what's going to happen? Those Q0s will cancel out. Then your electric field will become KQ divided by R square. So another alternative equation for electric field is K capital Q divided by R square. And this capital Q that we are talking about is the source of electric fields. Because in this question, in this setup, this capital Q is creating the fields, and then we place the point charge or test charge into the fields, and then we measure the force acting on it. And when we divide the force by the amount of charge that we have on the charge, then that tells us the electric field at that region. An electric field is a vector quantity, which means there's a direction. And what will be the direction of it? So point charge is a positive charge. So the direction of force acting on that positive charge in the field is going to be the direction of the electric field. So you have positive and positive. So what's going to happen? It's basically going to repel it. So the electric fields and the electric force are going towards right. And the unit for electric field is basically a force per charge, which is newtons per coulomb. All right, an electric field has a value of, so electric field is given as 7 times 10 to the power of 5. And a positive charge of, so Q that we are placing, which is the test charge, is 3 times 10 to the power of -5 coulombs. And place in the field, what force does the charge experience? So it's basically E equals force per charge. Q0 is basically the test charge, which is the smallest, but sometimes they are basically using different charges as a test charge, so that's also the same thing, so you don't need to worry about it. So we basically just try to solve it for force. So in this equation, force is basically electric field times test charge. So my force in that case is 7 times 10 to the power of 5 times 3 times 10 to the power of -5. Then 10 to the power of 5 and -5, they will cancel each other out. So the net force on that charge is going to be 3 times 7, which is 21 newtons. Alright, so electric fields are going to have their lines. So they're basically going out from the charge and they basically go to infinity. And direction of electric field lines. So if you are talking about a positive charge, they're basically the nice people. So they like to give everything out. So they would like to share everything. So they don't want to take everything to themselves. So the electric field lines from positive charges are going away from the charge. But the negatives are basically selfish. So they want everything for themselves. So electric field lines are basically going towards to negative charges. Alright, this is basically the direction of electric field lines. And if the charge is a point charge, electric field lines are straight and radially outward. So this is not going to be the only way of electric field lines that we will see. We will see a couple of others in the next slide. But these are basically for point charges. So if you have just one charge, then the electric field lines are basically going radially outward and they're basically straight and they go to infinity. And the other thing is line density represents the strength of the electric field. So let's say if we had, instead of just Q, if we had 2Q, then you would basically expect more lines going out of this guy. Alright, so line density is going to determine the strength of the charge. So more lines means more electric fields, so that's like greater charge. Alright, so if you have more than one charge in the system, then how do they look like? So in that case, what we need to know, electric field lines cannot cross one another. So they are not going to be touching to one another. So then we need to basically think about individual charges. They tend to go to infinity straight. But if, for example, think that they're going to go to infinity in this direction, and they are going to go to infinity in that direction. So as you can see, they basically cross one another. So that's not a possibility. Then they are not going to be able to do this. Then what do? They basically push on one another. All right. So they basically bend each other. All right. So if they're pretty close, then that's the behavior of like charges. And it doesn't really matter if it's positive or negative. If that was positive, this scenario, then what would happen? Electric field lines would basically go outward, because for electric field lines, for positive charges, they're going outward. But since they're negative, then the electric field lines are going to go towards the charge. But if they have positive and negative, then what's going to happen? again, they cannot cross one another, but this time, field lines are going to go basically, one, positive charges are going to send them out, but the negative charges are going to receive them. So in this case, instead of pushing on one another like this one, they're basically actually going to attract each other. So in this case, they are basically going to have this shape. All right. And those two, A and B, are basically cases when the charges are having the same amount. What happens if the charge is a different number? So then you are going to have similar things, but then what is happening over here? So as you can see, the first charge has 1, 2, 3, 4, 5, 6 lines, but the other one has a lot more than that. So then we can consider that this charge is greater than the first charge. And same thing for the second picture. And third picture, again, the first charge has less lines than the second charge. And in the last picture, first charge has more lines, so it is greater in charge, the magnitude. But the electric field lines are basically distributed with basically the same idea that they would do when they have the same amount of charge. Alright, so let's look at this one and determine the sign of the charges and rank them according to the magnitudes of their charges. So in here we don't have positive, negative, and we don't know the value of them. So number one thing that we know, negative charges are the selfish ones. So they're going to have all of the field lines toward themselves. So in this case, we are able to see that B is a negative charge. And A is basically sending everything out. So A is going to be a positive charge. So we know that for sure. And now, to be able to figure out their magnitudes, their strength, so what we need to look at basically the number of lines. So B has 1, 2, 3, 4, 5, 6, 7, 8 lines. And A has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 lines. So as you can see, A is greater in number, and it is also positive. So then B is going to be here, and A is going to be here. So A is greater than B, and A is positive, and B is negative charge. Alright, so that is it for electric field and forces. Thank you for watching. See you in the next video.